Sallay Talks.
Hello, everyone. We had a very interesting discussion with Polsha today, and I'm recording this video as my answer to Polsha, but actually I'd like to address it to everyone else because that's a very interesting topic. And I'd like to thank Polsha for her critical thinking. So critical thinking is basically asking the question why until you understand the nature of things. And I believe that's how mind of a scientist works. So you keep asking why until you find the beginning of things, the source of uh, until you get to the nature of things you study. So the situation was this: we were solving a problem, and I was explaining formulas and saying things like you just should multiply both sides by v, and v cancels out, and you can find your s at last. And Polsha said, please stop throwing these letters at me. Vs, tell me what I want to understand what's going on in terms of distance, speed, in terms of this actual problem that we are solving. Like what's going on in real world now. We just playing around with letters, and why can we do this? I don't get it. And that's a great question. So let me share my screen with you and share my ideas on this topic with you. I will mention these 5 rules that I'm stressing. Like last 2 weeks, I was fighting the whole school, trying to convince you guys that you should follow these rules when you solve a problem. You was opposing this, but that's a topic for another video. So what happens when we solve a problem? First, we are given a problem given in words, in a natural language, in human language. So we have problem given to us in human language, English, Russian, Spanish, whatever, natural language. So the first step is making a diagram. It helps us to understand what's going on. And the second step is write down a brief summary of a problem, this problem. And most of the school, a lot of students resist that. You find that that's a stupid, we can skip it, we can go without it. And actually, this is a very important step. So what happens here is we translate our problem from the language, from natural language, from human language to math language, language of mathematics, formulas, symbols, variables. So that's act of translation. Then we operate with this formal notation in math language using math rules. So doing mathematical transitions from one expression to another. So applying laws of logic. I will just call it doing the math. for this problem. And this is a very interesting transition. When we translate problem from our natural language to math language, we move from another to another dimension. There is no more plane flying over the surface of the Earth. There is no more like electron flying or whatever was happening in your problem. Now it's just the formulas you have. And that's a parallel dimension. There is, you can forget about the actual problem, and you just solve the equations that you've got. Like you moved from real world to the world of mathematical abstractions. And this abstract world of mathematics, it has its different laws, and these laws are never broken, by the way. This world is governed by strict logic. So you're doing the math, you're getting the result. And then you translate this result back to the natural language. Again. So writing down a brief summary is this step. Translating problem from natural language to math language, solving the problem in general form is math, substituting numerical values, well, it's still part of math, and giving the answer to the problem. So I ask you, and I believe I should be more strict about this rule, to give an answer in natural language. So if the question was, what distance did cyclist cover over some time? So the answer would be the cyclist did cover the distance of so many meters. So all these words together. Or what is the charge of the sphere? The answer would be the charge is number, not just number with units, but the whole sentence in natural language. So give the answer to the problem, formulate this answer in natural language is this moment of translation from language of math to natural language again. And when I think about, I didn't think about it this way before we had this conversation with Polsha, and I'm really grateful to her for her questions, because suddenly I see, and I can formulate this for you, the beauty of this process. We go in a parallel world, or the world of mathematics, where there is no more cyclist, there are no more spheres, charged spheres or real objects, just numbers and variables. We do the math, the mathematical things, we get some result, we translate this result in our real world, and we have a result, like some statement about real world again. So we begin with some information about real world, we travel in the parallel world, do some magic there, we get back to our world with new information, and we find out a new statement. And this statement is 100% correct. If we didn't do any mistakes during our translation, like here, if we didn't make any mistakes translating problem from natural language to math, if you didn't make any mistakes in math, and you can always check this, because for math you have formal rules to find any mistakes. And if you didn't make any mistakes translating back to natural language, you can be 100% sure that the information, uh, if the first statement about the world, if the first information, like problem itself, was correct, then your result is also correct. And that's insane. That's how physics work, actually. You can make statements about parts of the world that you can never witness. This is how we know about beginning of the universe, Big Bang. We make some observations, we translate them in this math language, we do some calculations, and we come to some results. And these results are 100% fact if we didn't make any mistakes on the way. So we can, doing this, going in the world of math and going back, we can make statements about parts of the world, about times that we can never witness ourselves. We can speak about the beginning of the universe. We can speak about the end of the universe, like how the sun will end. We know for sure that sun will die. We know when, and we know how. We know what will happen. That's magic. And this symbiotic relationship between math and physics and real world allows us to do this. So when we speak about solving physical problems, and this is my answer to our dispute, our dialogue with Polsha, you don't even try to understand what's going on anymore. Now math is going on. So you introduce some variables and you just solve equations. You forget if it's mass, distance, whatever. It's important when you translate from one language to another. It's important to understand like what is what. So you name this physical quantity with this letter, you name this physical quantity with this letter, you do the correct no, you don't make, sorry, words slip my mind sometimes. So you don't make any mistake. You create the correct model, and from that point you can forget the meaning of these letters. You just do the math like it's some abstract numbers, and yeah, you don't try to understand it, and you come up with some unexpected result, some results that and this result is actually true. So you can find out facts about real world without making experiments. So not without making experiments. So you make some experiment, you get some experimental data, then you go to this parallel dimension, make some conclusions there, and these conclusions can be applied to real world again. I think that's insane. That's magic of physics, and that's how it works. So thank you for your attention. Thank you, Polsha, for being a critical thinker and asking great questions that inspire me and allow me to understand and formulate new ideas about physics and mathematics. And thank you for watching.